is going on. Okay, let's see. Let me make sure I have Canvas open. Okay, I'm gonna share my screen so you can see my Canvas. Oh. Okay, so I'm in the other class's Canvas, but yours is gonna look the same. So I'm on the home page, and on the home page, we have the most recent announcements and your little to-do list. And then a little bit farther down, there's all the Zoom links. And then right above that is the weekly schedule. So the weekly schedule is the list of what's happening this week. And then as I have the recorded Zoom lectures, I attach that afterwards. So this right here will take you to the chapter 15 lecture. This one will take you to the when we talked about like the Beyond Labs, when we did the introduction to that. So on that weekly schedule tab.
Oh, okay. Thank you so much.
You're welcome.
Also?
Yeah.
I was wondering about for the test on when you were writing our sections for our defenses. On the top of each of the compounds, it gives a either like a boiling point or a melting point. Are we allowed to use as a defense? We found, say we found like compound 25, I think it's chemical X. Can I say that, oh, the correlated boiling point or melting point to chemical X via these online resources says that it matches as part of the defense? And
definitely.
Okay. And then does that mean that we have to have like a works cited page or something like that? Like, hey, we got like chemical information from this site or something like that?
No, because I mean, really, you can find boiling point and melting point just about anywhere. If you're citing like something else that might be a little bit more complex, you might want to include it, but it's boiling point and melting point. I mean, we can find those on Wikipedia for pretty much everything, so not a big deal. I would treat that information though as like secondary. So definitely use your graphs, and then like if you have like, even if you're like trying to choose between two compounds, or even just as, hey, this confirms my compound, then you can use that boiling point, melting point information as the kind of the secondary backup information.
Oh, absolutely. I mean, there is a plethora of other information that would hierarchy in terms of what is the best evidence versus what is the least important evidence, but just I wanted to know whether or not it could be added.
Okay, yeah, sounds good.
Professor, I have a question.
Yeah.
Regarding the exam, do we have to just turn in that, like the sample page with all the data and the charts, or do you want, like on the compounds, the compound list you gave us, those lines next to the graphs, do you need anything filled out there, or?
Nope, that was just for you. So I don't want those graphs back.
Oh, okay.
I have them, so I'll pull up the graphs on one page, or I have hard copies of all of them. But yeah, so what you're turning in are just the filled out tables. So on Canvas, it was labeled as the blank test page, I believe.
Right.
And so you're turning in one of those for each compound. So usually it ends up being just one page per compound. You might have gone on to a second page, but that's what you're turning in.
Okay, sounds good. Thank you.
You're welcome.
Would it be helpful because include, because I have a lot of work done on the compounds just because I'll be analyzing all the graphs, and then I'll be making notes on the sides, and then after that it would be, because then I would then usually kind of like do the assignments on there for like one for the HNMR and then one for the CNMR. Do you do you want any of that, or do you just, because doing all those things would get me to the structure, if that makes sense. So do you only just want the structure without all the labels and everything, and just I guess in its pure form?
You want us to show our work?
So I don't need you to turn in your work, because essentially the tables are showing me all of the data you've collected, and then your defense is telling me how you put all of that data together.
Okay.
So you can almost think of the defense as the pretty version of your work. You're kind of walking me through how you figured it out. In terms of the structure, your structure should be on there twice. Once with all of the letters labeled, and once with without the labels. So I'm going to the take-home test page here. And so on the example test page, see how it, oh, do I have to download it? It's not going to pull up. Okay. So I have the structure on my page twice here. Once with all of the carbons labeled, and so those carbons get, or not the carbons, excuse me, those labels get put into the hydrogen NMR table and the carbon NMR table. So I'm using the same labeling system, and I've labeled all the carbons, which means that label B and label E aren't going to be in the hydrogen NMR table because there aren't any hydrogens at those positions. But then in the carbon NMR data, we would use all of those labels. And then one more time, just without the labels, just so it's clear. And then it also gives me one to draw on if I need to.
And is it all right if you only give new labels to unique carbons? So
yeah, so I definitely could have labeled letter G. That could have also been letter C. And F over here could have just been another letter D. That would be completely okay also.
okay.
Okay,
Hey,
so
Professor.
yes.
So instead of just having one structure with all of the labels representing both the hydrogen, the HNMR and the CNMR, could you draw two different structures?
And have like two different sets of labels, you mean?
Correct.
You can, just make sure that it's very clear, because one of the problems, okay, the reason why I say that you should have one structured with one set of labels is because when students have done two structures with two sets of labels, there can be some flipping of information that as they put things into the tables. So I have found that if there's just one structure with one set of labels, the misinformation or the missing information is less common. So
Okay.
you can do it, but that is my warning to you.
Okay.
Okay, so before, I will ask you if you have more test questions in just a moment, but before we do that, we do have a guest with us today to talk about transferring. So go right ahead, Clinton.
All right, thank you. So my name's Clinton. I'm a specialist with the Transfer Center. I'm just going to give you guys some information on what we're doing while we're working remotely and how we can help you guys if you're starting to apply, thinking about applying, or whatever part you are at in the transfer process. So we do a lot of work before the application, during the application, and after. So we can help you plan. We can help you actually finish the applications, look out for any trouble areas in the applications. And then after you apply, if you guys don't know, there are some steps you need to take, but the application is for sure the focal point of transfer, but we do everything around it. And just because we're on virtual online, we're doing all the same services we normally would. We're still open our full 42 hours a week, I believe it is. So you can come talk to us anytime on transfer. Just because we're online doesn't really change anything. Pretty much everything we do translates online. So some of the services we have are workshops where they're structured around certain transfer topics, whether it's being ready to transfer, the overview of the transfer process, or more popular, which are application workshops, where you're actually getting to see the application be worked on or working on it in the workshop session and making progress on it, so you can know everything that there is to prepare for. For the applications, the biggest ones that we have are the Cal State universities and the UCs. both of the applications are pretty intuitive, but some things, you know, you just need a second set of eyes on, which is why we offer sessions where you can either come in to have them reviewed, do appointments to ask any specific questions on your application, where we can actually look at the application, make sure any problems you're having on the application are reconciled, just so you can submit an accurate application. When it comes to transferring, accurate applications are the best thing you can do to give yourself a better chance. There's no trick to transferring. You guys are doing the hard work now in the classroom. That's the biggest thing you can do to help yourself transfer. And then submitting an accurate application, which is where we come in, that's the other big thing you can do. Yeah, so there's no secret to having a better chance of getting in. It's just submitting the application the right way. So right now, we're in the tag application filing period, which if you don't know what that is, 6 of the UC campuses do transfer admission guarantee. Some majors will be restricted, but most aren't. And then there's different requirements you have to meet per campus. So all the campuses that do the tag are Davis, Irvine, Merced, Santa Barbara, Santa Cruz, and Riverside. So if you wanted to go to one of those schools and you have the right GPA for the schools, it ranges from a 2.8 to a 3.4, depending on the school, you can actually get guaranteed admission to one of those schools. So it's a really cool program. And I can tell you from my personal experience, it's one to take advantage of, even if you're on the fence. Maybe you wanted a backup school for UC. I personally used the TAG program to transfer from Saddleback College to UC Santa Barbara. Was never thinking about UC, really. Didn't really think I had the ability to do that, but I meet the requirements and I was in. So I can tell you from my personal experience, the TAG program is awesome and it's just as good as it sounds. There's no catch to it other than meeting the requirements. So we do workshops for that right now. We'll review those applications right now. Biggest thing for the application periods is the CSUs open October 1st and you have till November 30th to apply. The TAG application is open now till the end of September, and the UC application is November 1st to 30th. So if you're looking to start next fall, it's almost time to start applying. So we hope that you guys are gonna come see us and get some help on these applications, just so you can focus on what you're doing in the classroom and doing all the virtual learning, and we can help you make sure that you're submitting as accurate application as possible. So to touch on the UCs too, right now we have our UC, the UC Campus Week right now. So this is our homepage. I'm just gonna show you a few things on there and then I'll let you guys go. Right now we have our UC Campus Week. The UC is hosting them. Each of these schools are doing presentations, short 30-minute presentations just on what their schools are about. So if you're interested in a certain school, you know you want to transfer there, I recommend checking these out. If you're not sure on a school, but you want to learn more, another great opportunity to hear directly from the UCs. Something else that we have coming up on October 1st is our college fair. We're going to have 60 reps from different colleges. All the UCs will be in attendance. Most of the Cal States will be in attendance, and we have schools from far and wide as far as Alaska and Ohio coming. So that'll be a really cool event where you can get some more information on those schools. And our website is the place to go to get all of our information. So just look up the Transfer Center, go to sccollege.edu/transfer center. It'll take you to this page. Our contact information is here. Email is the one of the best ways to get in contact with us. We have our live chat. So anytime we're open, we have someone on our live chat. And then we also have appointments that you can schedule here. When you go a little further, you can see our workshops too. So this is the central page. You're going to find everything you can with transfer. And if you're not finding what you need, or you're just not sure where to start, go ahead and chat us or send us an email. But realistically, biggest thing to drive home is we are here just the same that we are in person. We're going to offer you the same services. And you don't have to go it alone when you're working on those applications. So come contact us. It's not just UC's, Cal State. We'll help you on any application that you're transferring to, just to give you that second set of eyes and a little bit of advising. So if anyone has any quick questions on transfer, I can answer them now. If not, then you guys can feel free to reach out to me. So does anyone have anything going on that they'd like to ask about? Anything from what I talked about?
If you send in an application and under the normal way, because you don't meet the qualifications for, say, TAG, but then you later fulfill the qualifications of TAG, is there basically a way to revise your application so that you have either?
So how it works for the TAG is you'll need the TAG requirements this month. So if you don't hit the TAG requirements basically now, or some schools have some GPA, where if you're not meeting the GPA or don't have a certain class, they'll extend it through fall, but only a couple do. Basically, if you don't tag now, you can't get the guarantee down the road. So September would be where you basically secure the tag, and you can't get it later down the road. So my recommendation is, even if you're on the fence about the tag, it's a free application and there's no essays or anything like that. Better to submit a tag that maybe won't get accepted than to not do it, because who knows, it's free. Unlike the UC application itself, where you have to pay $70 per campus and write essays, you don't have to do any of that for tags. So if you're way off the mark, then maybe not. But yeah, you can't get it unless you do the submission now. But that's a good question.
Wait, so you can still apply for tag even if you don't meet the prerequisites if you're like close to them?
It's basically, if you know for sure you're not gonna meet them, maybe look at a different campus as a backup. So if you don't hit the requirements, they're not gonna accept you either way. I should have explained that a little better. So basically, what I meant was, if you're close to a certain campus, but maybe you can tag at another campus. If you're gonna, you can only tag once and it's free. So tag at a campus where you can get in. Because it's free, doesn't cost anything. Sorry, I know I didn't explain that very well, but basically what I meant was tag somewhere that you can get into if you're gonna tag and meet the requirements.
Gotcha.
Any other questions for Clinton?
And we can find all these applications on the transfer site?
Yes, so all that information should be hopefully readily available on the website. And if you're having trouble finding it, you can reach out to us and we can guide you on there. But yeah, basically if you Google it or go to our website, you'll be able to find them.
So you were talking about how some majors aren't, like, it's not a guarantee. Would those majors be listed for each school?
Yeah, so each school is going to have their specific tags. So if you just look up, so like say if you were looking at Irvine, just look up the UCI tag requirements. They'll have their restricted majors, the GPA you need, and what classes, specific classes that you will need at a certain time. It's usually their English and math needs to be done at a certain time. But yeah, they'll say very clearly on the website that they don't take certain majors.
Thanks.
Yeah. Well, that's about all I have for you guys. And find us on our website, email us, live chat us, set up an appointment. And if you have more questions that come up, definitely let us know.
Thank you so much.
All right. Have a nice day.
Okay, so yeah, definitely take advantage of the services on campus. Things like this can be confusing and hard because you've never done it before. I listened to, I think it was in a podcast I listened to this weekend, but a woman was talking about when she was first going to college and it was her freshman orientation. So they were, graduating seniors, new freshmen. They were all blindfolded and put into this maze made out of ropes. And they were told, if any point you need help, just raise your hand. And so as she was in the maze, you couldn't see if other people were asking for help. And I got to the end and it was just her and one guy left. But it turned out that the only way to even get out of the maze was to ask for help. So the whole idea is that you don't know the maze. These other people do know the maze. They are there to help you. And I know I'm included in this group, but I know that some of us are very stubborn and don't always like asking for help. But there are people there. That's their job.
I get a knife and I cut the rope.
Exactly. Oh, actually, before I was going to switch over to slides. Before I switch over to slides, any general questions about the test? So not like about your specific unknown, but any other questions? What's that, Justin?
I was wondering, what are my unknowns?
Oh yeah, they're all methyl with 1 chlorine.
Heck yeah, I knew it. I knew they all looked the same.
Any test questions for me? Can we draw the structures with an Apple Pencil like by hand? Definitely. So drawing the structures, you can do it digitally on your tablet. You can download some software. The software that I personally use is called ChemSketch, and it is free, so you can download that. There's also a lot of just web-based drawing programs, so you don't have to download them. If you Google organic chemistry drawing, you'll find a bunch of them. You don't have to do it by a program or digitally though. And so even if you draw it on a piece of paper and take a picture of it and then like embed that picture, you can do it that way too. Or if you find your structure and look on Google Images and then just copy and paste it over, that will work for this too. The only time that you have to use the drawing program is when you do your formal report. And I'll put an announcement up when we get much closer to that, and give you some links for drawing programs. Is it possible to print? So is it possible to print and fill out by hand? If you have very nice, pretty handwriting, that would be completely okay. And then, scan it, upload it for me. You could also print it and just draw the picture on it and then upload it. Well, I guess you'd need fillable PDF at that point. But yeah, you can print it and do it that way. That would work.
Also, do you want all the PDFs like merged together, or do you want them separate? Or?
Merge them together. It definitely makes it easier to go through them and grade them. Canvas is weird. The grader on it's weird. So if there's more than one PDF, I can't write on one PDF and then switch to your next one. It's not the most user-friendly.
Okay, thank you.
Just to confirm, it's just the tables, right?
Yeah.
Just times 4.
Yes, exactly.
Okay.
Yeah, make sure that your unknown number is on there as well. I have had students in the past not put their unknown number on there, and then I don't have anything to compare it to. Anything else? Okay, so as I'm pulling up my slides here, 2 things I know I want to mention. One is I did get a text from somebody just not that long ago about the wait times for DLAs today. So I don't know if that was one of you guys or somebody from the morning class. So I did extend the deadline for the DLAs till Wednesday, but it is something I want you to be aware of, how long the wait times are, because that's really not going to change as the semester goes on. So you just have to work on them early, not the day they're due. And then the second thing is the last Friday was the first round of goggle, lab coat, drawer stuff pickup, and I heard it went well, and the lab tech that was out there gave our class lots of compliments because she said that you guys were all very friendly and very nice, which was nice to hear, and no surprise. But there is one more opportunity. So the other one is this Friday. I'm going to send out an email just as a reminder. But if you haven't signed up for this Friday and you still want to pick up your stuff, then email me back with the information. So I'm making myself a note right now to email you guys out the time and the information that I will need. Okay, that's enough. There'll be other options for extra credit available. So it's mostly just the DLAs. There was like the very first assignment you guys did where you had to essentially like practice uploading. That was extra credit, and there might be little things here and there, but definitely the bulk of it is the DLAs. Okay, chapter 16. Yes, the max extra credit is 50. That is correct. So, and I don't think that I want to say there's 9 DLAs. And so with the extra credit that you guys all did already, that's the 10th thing, or the 50 points. So if you that would be the maximum. And then I might add in extra little things here and there. Usually on tests, there might be 1 extra credit question. If there's extra credit like on a test, that goes into your test points though, so that doesn't actually count against you in terms of your maximum extra credit points, because I don't add it into the spreadsheet separately. All right, chapter 16, conjugated pi systems and pericyclic reactions. So our next unit is chapter 16, 17, and 18. 17 and 18 are all about benzene, And chapter 16 is somewhat of an introduction to that, because we're going to talk about just when we have like two double bonds together and what we make. And then the second half of the chapter are the pericyclic reactions. So they're a little bit different, and we'll probably get to like an introduction of those today. So let's see how far we get. So it is a new chapter. So we are starting with a little bit of vocabulary. And what we're focusing on in this chapter are the conjugated double bonds right there in the middle. And we can label something as conjugated if it's separated by one sigma bond. The opposite of that, or the other option then, is if we have an isolated double bond, which is separated by two or more sigma bonds. And more importantly, it's separated by at least one sp3 carbon. So we know resonance qualifications are that something has to be sp2 or sp hybridized in order to go through resonance, because it has to have that available p orbital. Conjugated double bonds have resonance. So if we look at a conjugated double bond, we can do this. And this is why they get their own chapter. And we end up with a negative and a positive, but isolated double bonds can't do that. And so because they can't do that, they just get put into their own category. And way back when, we did an entire chapter on alkene reactions. That's where isolated double bonds would fall. Conjugated double bonds react a little bit differently because they have that resonance, so they get their own chapter. And then that first one on the left there, cumulated double bonds, these are when we have two double bonds that are back to back. So we have a CH2 double bonded to a carbon, double bonded to a carbon with a methyl and a hydrogen. So this little dot in the middle, that's representing the carbon that's double bonded on both sides. We wouldn't just want to put double bond, because it doesn't quite look like there's anything there, or it looks like you drew just a really long double bond. So it's just to kind of make it very clear that there's two separate double bonds with a carbon in the middle.
Professor?
Yeah.
Is that something called an allene, or is that something different?
That's not something different. It does fall into that category, an allene. It's kind of the difference between, let's see. So when we have an allene, it's like referring to a substituent off of something else. Just like when we talk about like an allyl group is like these three carbons right here. So when we have an isolated system, it contains allyl groups. So it's another way to refer to it in relation to something else.
Got it.
So not the most clear definition, but it's really kind of what you're thinking of as a parent chain versus what you're thinking of as a substituent. Our conjugated systems can contain heteroatoms. So our picture that's right down here, this conjugated enone, we have just that one sigma bond in between our two double bonds. One of the double bonds happens to be a carbon-oxygen double bond. That's completely okay. It's still going to have resonance. The name of this is an enone. Ene because it's an alkene, and one because it's a ketone. So we do that often in organic chemistry. We combine their names. I think it's useful because hopefully it can help you see what it's made of. Let's see, I think we talked about everything else on there. Yeah. So let's talk about how to make these. We have one reaction on here, but really two different ways to do it. So our starting material in our first reaction is an allylic halide. So let's do a little refresher on a couple terms here. When we have a double bond, the two carbons that are in the double bond are called vinylic carbons. That can also be referred to as a vinyl group. And then, oh, there we go. Click the wrong button. And then any carbon that's attached, so this one and this one are the allylic carbons. So definitely words that should ring a little bit of a bell. We definitely talked about them, or your other teacher, whoever you had, should have talked about them, but just a reminder. So we're starting with an allylic halide. We're going to react it, in this case, with tert butoxide. So this needs to be a strong, bulky base. So it doesn't have to be tert butoxide, but tert butoxide is probably the most common, and it's definitely going to fulfill both of those categories of being strong and bulky. We'll talk about the why on the next page when we look at the mechanism. And again, just a little bit of a reminder on this guy. So that means this is a tert butyl group attached to an oxygen that is negatively charged. The potassium is just there as a counter ion, to balance out that charge. So you might see it with sodium instead of potassium. You might also just see it written as TBUO negative without that counter ion because it's doing the same job. So any of those are going to work. And then what we create is that conjugated diene. And then on the second reaction that's down there, the second version of this reaction, we are starting with a vicinal dihalide. So another reminder then on that term vicinal. When we have two substituents, and it can be two of anything. It could be methyls, it could be hydrogens, it could be alcohols. The term vicinal refers to two substituents, or excuse me, the term geminal, skipped ahead there. Geminal refers to two substituents on the same carbon, and vicinal is two substituents on adjacent carbons. So again, we give structures like that terms so we don't have to say two bromines on two carbons that are right next to each other. Instead, we can just say vicinal bromides. Again, we're reacting this with a strong bulky base, and again, we're making a conjugated diene. So let's look at the mechanism for this. And I'm going to use the first one as my example as I go through this. The second one's going to go through the same mechanism, but twice. So here is my allylic halide, and I'm going to react this with my tert butoxide. And I'm going to draw in my hydrogen here. We're going to start our arrow going from the oxygen to the hydrogen.
Professor, and you're just choosing not to include the potassium?
Yeah, it's not part of the mechanism, so it's not something we would need to draw in.
Okay, thank you.
So my arrow's starting at my oxygen. It's starting where a lone pair would be on that oxygen. We know it's there. We don't have to actually draw it in, but it's starting at that lone pair. And I'm going to label these types of steps. This isn't something I'm going to do for every mechanism, but this is our first one this semester. So this is a proton transfer. So remember back in, man, I want to say chapter 6, but I'm not 100% sure on that. One of the chapters we talked about mechanisms and the different types of steps, and proton transfer was one of them. And to go along with that proton transfer, what the arrow we've drawn so far just shows the bond between the oxygen and the hydrogen. Yeah, Nathan, go ahead.
Professor, I was just wondering, do you test on mechanisms?
Yes.
Okay.
Yeah. So our arrow right now shows the bond forming between the oxygen and the hydrogen. We know hydrogen can only have one bond. So we're going to take those other electrons between the hydrogen and the carbon, and we're going to create a pi bond. So that second arrow makes the new pi bond between the two carbons. But if we just left it at that, carbon number 2 of that chain would have 5 bonds. So we need to do one more arrow. We're going to kick this bromine off. And so that last arrow then, that is the loss of a leaving group.
Professor?
Yeah.
So I've noticed that you didn't draw the lone pairs for the tert butoxide, and I remember last semester our professor urged us to ask the next professor like how specific you are on like mechanisms, because I remember he was very specific, and if we didn't draw the pairs and the arrow in the exact place, he would take points off.
So I do not think you need to draw in the lone pairs. But in terms of specificity, your arrow should start at the oxygen. So whether you start it here or here or here, all of those would be okay. What would not be okay is if you just like kind of started out here, like too far away. So that's a bad one right there. I'll put a little no through that. So just start it so it's next to the oxygen and not too far away, but you do not need to actually draw in the lone pairs. And yeah, it is funny because that is one of those topics that is debated amongst organic chemistry professors. I'm in a Facebook group for organic chemistry professors, and that's one of the things that was just asked, is if that's required. And I'm actually in the minority on that one. I'm not as strict as other people. All right, product then, we end up with our 2 double bonds. If we looked at this same example, but for the second option, we would just go through the same process twice. Now, you have seen this mechanism before. Do you remember why you've seen it before, or what other name we've given it?
Elimination.
Yes. So is it an E1 or an E2 mechanism?
E1?
It's an E2. So you had a 50-50 shot, but it is an E2 mechanism. And so the 1 and the 2 are essentially telling you like how many things are happening at a time. SN1 and E1 both form carbocations because their leaving group leaves, and then we do the second thing. So this is an E2 mechanism. So that's going back to chapter 7 when you guys had all of that stuff in competition with each other. So SN1, E1, SN2, E2. Now, one of the things we said we needed for this was that strong, bulky base. That strong, bulky base is going to prevent SN2 reactions from happening. So we're specifically tailoring our reagents and our starting material so that we don't have any other competing reactions. There's only the one reaction that's going to occur. Checking to see if there's anything else I was going to say. Nope, my notes literally just say mechanism. My notes are useful to nobody but me. Questions on the mechanism? Okay. A little bit of background information on our double bonds. So when we look at bond length, a single bond between 2 conjugated double bonds has a bond length of 148 picometers, and just a regular old single bond is 153. The reason behind this is because of the hybridization of the carbons. So we have sp2 versus sp3. When we look at an sp2 hybrid orbital, it's made up of one s orbital, which remember is the sphere. Wasn't a very pretty circle. And then one p orbital, which is, we use the term dumbbell to describe it. So that means that an sp2 orbital is 33% s, because it's 1 part s, 2 parts p. And an sp3 orbital is 1 part s and 3 parts p, so that means it's 25% s. All right, why that matters, why we care about that, is because the sp2 orbital, because it has more s character, the percentage of s is higher, it's going to make that orbital closer to the nucleus. Because an s orbital in general, because it has that sphere shape, is more condensed and closer to the nucleus, so the hybrid is going to also be closer to the nucleus, which will make it have a shorter bond. So these are also ways that these are also like pieces of evidence that we can use to support hybridization theory and the conjugation stability, because we can measure these bond lengths. These are things that can be figured out, and then because these two single bonds have different bond lengths, our other theories like Vesper theory, our hybridization theory, can help explain that. And then the last thing on this slide is looking at S-cis and S-trans. So this isn't looking at whether the double bonds are cis or trans, it's looking at the single bond. So when we look at that single bond, are the double bonds cis to each other or are they trans to each other? And this double bond has free rotation. So notice that we have our equilibrium arrow, so it can rotate back and forth. The trans is going to be more stable, which is probably not a surprise. We definitely see trans being more stable when we look at double bonds as well, because it's just kind of pushing things away. It's pushing sterically hindered groups away from each other. But just because the trans is more stable doesn't mean the cis doesn't exist. They are in equilibrium, and sometimes the cis is the only one that exists. For example, in a ring, we don't have rotation. So within a ring, those conjugated double bonds are only going to be in the cis formation because they're locked into place. So that is something that will come up a little bit later on. One of the reactions we're going to look at will only happen when it's in the cis formation. This slide is also telling us that our conjugated double bonds are more stable. So how it's telling us that, we have energy over here on the y-axis, and we have just our plain alkane down here as a product. And then the two reactions that are represented, we have our single alkene here reacting with hydrogen. So we know this reaction. We react an alkene with hydrogen. It's going to add a hydrogen to each of those vinylic carbons and create an alkane. Notice that it's happening twice though, so we can react two alkenes. And then on the right-hand side over here, we have our conjugated diene. And we only have one of those because they already have two double bonds each. So in total, we're reacting the same number of double bonds. When our regular alkene reacts, it's going to release 254 kilojoules of heat. And when our conjugated reacts, it releases 239 kilojoules of heat. And they're both producing the same product. So the reason behind the difference between, the reason behind that 15 kilojoule difference is because our conjugated diene started out at a lower energy level already compared to our alkene. And so it didn't have to release as much energy to get down to the same place. So all of this is saying that conjugated dienes are more stable than isolated alkenes. And the proof behind that is this heat of hydrogenation reaction data. We need to have a crash course on molecular orbital theory. So this is a theory that you have probably spent short bursts of time on. In general chemistry, you learn about Lewis theory, and you learn about Vesper theory, which is hybridization in the shapes. And then usually towards the end of that chapter, your teacher will spend just a couple slides on MO theory. And then in first semester organic, we touched on it a little bit here and there. It also kind of depends on who your teacher is, just how much time gets spent on it. And the same thing's kind of going to happen this semester. We'll come back to it as we need to. One of the reasons we don't usually spend a whole lot of time on it is because it doesn't work as hand in hand with the other theories as nicely as they work together. So when we draw a Lewis structure, we can look at each individual carbon and we know its geometry, we know its hybridization. Those two theories work really well together, and every time you're doing organic chemistry, you're using them. You're obviously not thinking about it from that perspective, but when you draw a structure, that's a Lewis structure. You're basing it off of that information. MO theory doesn't come into play. So it's its own little thing. It's very complex in terms of the math behind it. So we're definitely looking at a surface level, dipping our toes into the MO theory pool. So this slide is intended to give us a reminder on the terms and the acronyms. And then the next couple slides, we're going to look at how to apply this to our conjugated dienes. So our diagram there is a molecular orbital diagram, or an MO diagram. There's essentially three parts to it. On the sides, so right here that I've circled in purple, these are AOs, which stands for atomic orbitals. So these are representing the atoms before they've bonded. In the middle, so right down the middle here, these are the MOs, or the molecular orbitals. So these are representing the orbitals after the atoms have come together. So the atoms become, after they form bonds, become molecules. And then the number of AOs is always equal to the number of MOs. So in this example, we have 2 AOs and we have 2 MOs. And half of the MOs will always be higher in energy than the AOs, and half of the MOs will always be lower in energy than the AOs. So when there's only 2, that's nice and easy to see, because we have energy over here, and we have our MO on the top that's higher in energy, and the one on the bottom is lower. The one on the top is always what we refer to as an antibonding MO, and the one on the bottom is a bonding MO. Antibonding MOs also get labeled with a star sometimes. It kind of depends on like why you're seeing it. So if it's a test question, you might not have a star there because it would give away extra information. But if you do see ones labeled with stars, it's because they're antibonding. Looking at the rest of my notes here. When electrons get put into them, we do it in the same way that we have done with other electron configurations, meaning we start at the lowest energy and work our way up. So when we look at the AOs, each one has 1 electron. And so at that bonding, that low energy molecular orbital, we put those electrons into that orbital, and then we're out. We don't have any more electrons. So a bonding molecular orbital is essentially what we think of when we think of bonding. We take one electron from one carbon, we take one electron from another carbon, they come together, and now we have a filled orbital. So we're taking two half-filled orbitals, overlapping them, and creating a filled orbital, creating a bond. The orbital on the top, the one that's labeled as antibonding, doesn't really have anything equivalent to it in our other theories, which is one of the reasons why it's difficult to utilize this information. The best way to think of it is if we had our electron and then our other electron was also pointing up, so they're pointing in the same direction. We can't put two electrons in the same orbital if they're pointing in the same direction. So when they get close to each other, instead of forming a bond, they're actually going to repel each other. And so because they're repelling each other, what we end up with is a node. A node is a space where there is zero chance of finding an electron. So it's essentially a void of no electrons in the middle there. The number of nodes increases as we go up. So this one only has 2 MOs, but if we had more, it will increase as we go up the list. And we'll look at some with more. The last two acronyms on here are Homo and Lumo. And these are frontier orbitals, which really is just a way to say that these ones are important. So they get their own names, they get their own labels, because this is where the action is going to take place. These are where bonds are going to form. So Homo stands for highest occupied molecular orbital. So this is the molecular orbital that has electrons in it. So that's what the occupied part means, has electrons. And when we say highest, we mean highest in energy. So this is the molecular orbital with electrons in it at the highest possible energy level. So that would be this one. And then LUMO is the lowest energy level orbital that is unoccupied, so no electrons. So that means this one is the LUMO. The HOMO and the LUMO are always going to be one after another, because if this orbital is my highest energied orbital with electrons, that means the next orbital is not going to have electrons in it, but it will be the lowest energy orbital that doesn't have any electrons, because as we continue on, they're going to get higher in energy. So the LUMO is always going to be right above the HOMO. They always go together in a pair like that. And then the last bullet point on here says excited versus ground state. This goes along with other times we've talked about excited and ground state. Ground state is the lowest possible energy level of all of the electrons. So essentially their location when they're at the lowest energy level. And then excited would be if they absorb some energy and they get bumped up to a higher energy level. So essentially the same idea that we've seen in other structures.
Hey, Professor.
Yeah.
Would you mind explaining why the top one was LUMO and below it was HOMO again?
Yeah. So, and this might make sense when we see something bigger also, but the bottom orbital has electrons in it, so it's an occupied orbital, and even though it's the only one, it's the highest energied orbital that has electrons in it. And the other one doesn't have orbital, so that makes it unoccupied. And it's the lowest energied orbital that is unoccupied. So in this case, we only had 2 to choose from. But when we look at a larger one, it might make a little more sense. Another way to tell is wherever our atomic orbitals are, we can draw kind of our starting energy line. The anti-bonding orbitals are always going to be above that line. And the first one will be the LUMO. Below that line are always going to be the bonding orbitals, and the first one will always be the HOMO. So we can always kind of draw that halfway line wherever the atomic orbitals are, and then anti-bonding's above, starting with the LUMO, bondings are below, starting with the HOMO. Okay, let's look at something bigger. So we are now looking at 1,3-butadiene. And we're looking at the 4 carbons within this structure. And specifically, we're looking at each of their unhybridized p orbitals. So these are representing the atomic orbitals. We don't have them on the other side, really just for space reasons. And a lot of times we don't, even though the atomic orbitals belong on the sides, we don't always draw them in. What we care about is the middle part. We care about those molecular orbitals. So if I draw my line right here, I know that number 1 and number 2, so see how they're numbered right here, these are my bonding MOs, and number 3 and number 4 are my anti-bonding MOs. Anti-MO, there we go. We have 2 graphs, so the graph on, or not graphs, but diagrams, the diagram on the left and the diagram on the right are showing us the exact same information, just in slightly different ways. So I'm actually going to focus on this one, because this is going to look more like what you would see on a test. So we have our 4 electrons in there. 2 of the electrons are in MO1 and 2 of the electrons are in MO2. We know that 1 and 2 are bonding. 3 and 4 are anti-bonding, so I'm giving them little stars. Let's see, what else do I have on my little sheet here that I was going to talk about? Oh, so let's look at how many nodes they each have. So the very first one does not have any nodes. The next one has 1, the next one has 2, the next one has 3. Now these are labeled, they're telling us how many nodes, but we can also see it in the drawing. So notice in the first drawing, it's blue on top, so they can completely match up and overlap, and red on the bottom. So it's overlapped all the way across, good sharing of electrons. What this is representing is the resonance hybrid. So if I draw in my resonance contributor for this structure, those are my 2 resonance contributors. The resonance hybrid then is going to look like this, where the electrons are overlapped between all 4 atoms. So that first molecular orbital is essentially a representation of that resonance hybrid, where the electrons are being shared all the way across the structure. The second one, now we have 1 node in between. So on the left side, the blues are on top and overlapping, and on the right side, the blues are on the bottom and overlapping. So this is essentially representing our original structure. So this is number 2, this would be number 1. Because we have 2 isolated double bonds. They're not interacting with each other. There's a node in between them, but we do have those 2 isolated double bonds. And then on the next one, we have that overlap in the middle, but the 2 on the edges aren't participating, so we end up with these 2 nodes. So that's kind of this one, which would make sense. It should be a little bit higher in energy because we have the charges. And then the last one with 3 nodes where nothing is interacting, if we take this structure and we essentially do this. So this is not a good resonance contributor. But we get that. We have 4 isolated p orbitals that aren't interacting with each other. Sometimes we can draw structures like that to help understand the nodes and the orbitals. Sometimes we can't because there's too much complexity going on and it doesn't quite make sense. This one's a good one to look at though, because it's as small of a structure as we can get and still have those conjugated double bonds. and it's a good way to represent it. Number 2 here is the HOMO orbital, the highest occupied molecular orbital, and number 3 is the LUMO.
Professor, I have a question.
Yeah.
What does antibonding mean that there's just no electrons present in the orbital state?
Not necessarily. Antibonding really just means that it's higher in energy than where it started. And it started in energy, switching colors here. It started in energy right here. This is our starting point. If the AOs aren't drawn in, we can always just cut it in half. There's always going to be an even number. So half of them, the top half will always be anti-bonding and the bottom half will always be bonding. It really is an energy definition.
Okay, thank you.
You're welcome. Anything else on these? Okay, so we're going to do one more. So this would be more like what you would see on a test. So we essentially have an empty MO diagram. It's not filled in. And we're going to look at the MO diagram for 135 hexatriene. So that's what it's telling us over here on my title that I had to flip on its side. So 135 hexatriene. So there are 6 carbons that are participating in all of those double bonds. So that means 6 atomic orbitals, which means 6 molecular orbitals, which is what we have. So the first thing we're doing is we're filling these in. So that means we're showing the overlap between them. So I'm just going to color them in with purple. I'm only doing purple, so that just means we're going to have purple and white. So the bottom one is going to have complete overlap. So 0 nodes. And this is going to be the same pattern you will see no matter how many carbons. The first one always has 0 nodes. And then as we go up the list, it will increase by 1. So I know that this one has 1 node, 2, 3, 4, and 5. So once you know that, you can fill in the pattern for the most part pretty easy. There's a couple of them that can get a little bit tricky. The molecules stay pretty symmetrical. So right down here in the middle, that's the node. So on the left-hand side, I'm going to put the purples on the top to show that they're overlapping. And on the right-hand side, I'm going to put the purples on the bottom to show that they're overlapping. But the 2 halves are different because they're not overlapping between the 2 halves. And then when we have 2 nodes, we're splitting it into thirds. So we'll have overlap, overlap, and overlap. When we get to 3 nodes, we're going to have this pattern. So we essentially want to keep as much overlapped as possible. Now, another way to look at this, or another pattern to see even, is if you look at how many groups are overlapped. So in the first one, I could say that there's 1 group that's overlapped because they're all overlapping. And in this one, there's 2 groups that are overlapping. And in this one, there's 3 groups that are overlapping. So on the next one, I will have four groupings. So I changed how I phrased that a little bit because there's not going to be as many overlaps. But it does get broken up into these 4 groups. So we do have overlap in the middle there. Right there, right there. But we do have the isolated ones on the end. And then as we go to the next one, we will have our 4 nodes. So the only overlapping is going to happen right here in the middle. And then we have the 2 isolated ones. And then, excuse me, the first one, everybody was the same and overlapped all the way across. On the last one, every single time, they're all going to be opposites, and there's a node between each orbital. So the first one and the last one, no matter how many carbons are involved, are always going to look the same. Rested my arm on the keyboard. So we have our nodes labeled, the number of nodes. We have it filled in. Where would I draw my divider line between the bonding orbitals and the anti-bonding orbitals? So using the numbers that are over here on the side, so 1, 2, 3, 4, 5, 6, between which 2 orbitals am I going to draw my line between bonding and anti-bonding?
3 and 4.
Good. So let's see, I'm gonna grab a different color here. So we're gonna go between 3 and 4. Up this way are the anti-bonding, and down this way are my bonding. And it's always going to be at that halfway point. You're never gonna have an odd number, so it will always be even because they're double bonds. So you have to have, they have to come in pairs of carbon, so it will always be an even number. And then which numbered orbital is the HOMO orbital?
3.
Good.
Hey, Professor, I have a quick question.
Yeah.
The blue lines, that's the overlapping, you said?
Yeah, so just showing that because the colors are matching up, that's how we will get those p orbitals overlapping with each other.
Got it. So would number 5 have an overlap?
Yes, yeah. So number 5 would have the overlap just right there.
Cool, thank you.
You're welcome.
Sorry, one more quick question.
Yeah.
For row 4, could you have drawn the nodes a little bit different where the line, like the 2 overlap would be on the ends, on each end?
So I'm going to answer your question a couple different ways. First answer is this is the correct way to draw it. If this was a test question though, and you drew it with the overlap on the ends and the isolated ones in the middle, I would count it as correct because you're showing the right amount of overlap and you're showing the right amount of nodes. So I don't expect you to have like those specific patterns memorized, but you should know how many nodes you're gonna see. Does that make sense?
Okay, yes, thank you.
Yeah, and when in doubt, if you look at orbital 4 and orbital 5, notice that the ones that are isolated are on the ends, and then the overlapping ones are in the middle. So that can sometimes help you figure out the pattern you're supposed to draw to. Which orbital, 1 through 6, is the LUMO orbital?
4.
Good. Any other questions on our MO diagram here? Okay, so the reason we talk about this is 2 reasons. One, it does actually show us why our conjugated double bonds are so stable. So in that very bottom MO, showing that full overlap all the way across helps show their stability because of the resonance. And 2, a second reason why we look at this is one of those pericyclic reactions, which we'll get to on Wednesday, I think, because what time is it? 3:05. Yeah, we won't get to it today. We will look at how 2 molecules come together by looking at their MO diagram. So it is kind of it's definitely a small part of the chapter, but knowing these labels on the MO diagram, they do come up throughout the semester, and so it's just kind of a good reminder as well. All right, we are moving on then to reaction number 2. So in this reaction, we are reacting our conjugated diene with HBr. So let me give some word labels here. Do not know why that line is showing up on the bottom down there. Okay, conjugated diene. And we do have it shown with HBr, but this could also be HCl. It could also be Br2 or Cl2. Those will both do the same thing as well. And we're making 2 different products, and these are labeled as the 1,2 product and the 1,4 product. And the reason for that is if I number my carbons, I'm going to number 1, 2, 3, and 4. In the 1,2 product, the hydrogen's adding to carbon number 1, the bromine is adding to carbon number 2. Now this could be a really long chain. There could be other stuff happening. We're only numbering the 4 carbons that are part of this conjugated diene system, so it doesn't matter what else is happening. In the second product, my hydrogen, again, is adding to carbon number 1, but my bromine gets added to carbon number 4. So let's talk about why we get both products. The 1,2 product is the same as what we've seen before. If we react that with HBr, and I think this was the very first reaction we learned in first semester, we make this. So that's essentially a reaction we've seen from the start. The 1,4 is what makes it a little bit different. Here's our intermediate. I'm going to do a little erasing here. Do a little moving. We have our conjugated diene. It reacts with the HBr, so it's grabbing onto that hydrogen. Bromines are leaving group. We create this carbocation intermediate. And it is resonance stabilized. So there's 2 things that can occur here. The first thing that can occur is our bromine can do a nucleophilic attack at that carbocation, and when that happens, we make the 1,2 product. So the hydrogen adds, the bromine adds. Essentially the same mechanism that we've learned from the beginning. The second thing that can happen though is this arrow right here is showing us the resonance. So this is an allylic carbocation. This falls into one of our resonance categories, that pi bond next to a positive charge. So the pi bond scoots over, and now our carbocation is on our carbon number 4. So we can do the bromine attacking that carbocation, and now we get the 1,4 product. So the 1,2 addition is just a simple, we add a hydrogen, we add a bromine. The 1,4 addition is what occurs if resonance happens in between the 2 steps. So let's look at a little practice problem. We're going to look at this and this and this, and we're going to react it with HBr. And I'm going to draw out the mechanism as we go through this. So let's see. I'll do a little erasing here so I can draw the bond in between. So I'm going to start from my double bond right onto that hydrogen, and we're going to break that hydrogen-bromine bond. And what we end up with is a hydrogen right here and a carbocation. And I still have my pi bond. And I am going to just draw that exact same thing one more time since we already know we're going to have to use it twice. Now, the first thing that can happen is I have my bromine. We're going to do a nucleophilic attack at that carbocation. So if that occurs, the first product we're going to draw is and I am drawing my hydrogens in just to emphasize where they're at, but the bromine adds where that methyl group is, and that second double bond stays in place. So this is my 1, 2 product. And I'm going to number my carbons just so we know who is who, but there's 1, 2, 3, 4. So again, there's other carbons in that ring. There's the methyl substituent, but they're not part of the reactive group of carbons. So we're not numbering them. We don't care where they're at. Well, we care a little, but they're not participating. In my second pathway, I'm going to move the pi bond right there. I'm putting brackets around this because that's what we do with resonance. And then my second structure, after we go through that resonance shift, the hydrogen stays where it's at, the methyl stays where it's at, but my pi bond has now moved right there, which means my carbocation has moved right there. I still have a bromine hanging out. Now my bromine is going to do the nucleophilic attack, but my carbocation has shift locations. So my new product we have the hydrogen up here at number 1, the methyl still where it belongs. My double bond has moved, and now my bromine is over here. So this is my 1,4 product. Now, technically, there's more products to this. I started at carbons 1 and 2, but I could have numbered it the other way around. I could have started at the bottom and numbered it going up the ring. And because it's not completely symmetrical, there's not a methyl on carbon 3 as well, we would have gotten different products. The reason why I started there is because the very first carbocation that I made is a tertiary allylic carbocation. If I would have gone the other direction, I would have made a secondary carbocation, and we know that tertiary is more stable. So I started with the pathway that was already going to give me higher stability. If the question asked you to draw all the possible products, though, then we would need to do the other one. But what we want to talk about next, where this is headed, is which one of these is our major product? And really, it's going to depend on the temperature that the reaction is done at. So here's the same reaction we started with on our reaction slide. We do the reaction at 0 degrees Celsius, so we know that that's freezing, and at 40 degrees Celsius. So room temperature is like 25-ish. So 40 Celsius isn't a lot higher than that. And I'm pointing that out because it doesn't mean that we have to heat this at extreme temperatures. It just means that it needs to be warmer than room temperature. And so when we see this on the arrow, it might just say cold. It might say 0. Instead of 40, you might have a different number. But you might also just see the triangle because we know that means heat. At cold temperatures, the 1,2 product is our major product. And at hot temperatures, the 1,4 product is our major product. Let's talk about why. So this is our reaction coordinate diagram. We have energy over here on our y-axis, and the x-axis is labeled as reaction coordinate. I tend to think of it as time passing. So over here, we have our starting material, we have our reagent, and then over here, we have our 2 products, and then in the middle, we have our intermediates and our transition states. So it's really just kind of showing the reaction progressing. So this is showing both pathways. The blue pathway is the 1,2, The red pathway is the 1,4. So the first step is the same for both of them. The hydrogen adds to our double bond and we form a carbocation. And then here's where the differences take place. So let's talk about the 1,2 first. With the 1,2 product, the bromine bonds to that carbocation, and that's it. We form a product. So look at the height of the hill. Remember, that's called the activation energy. And so the activation energy for that 1,2 product is a lot lower than the activation energy for the pathway for the 1,4 product. And it's going to come into play. So then if we look at the other pathway, to do the 1,4, we have to start with some resonance. We make a new intermediate, then our bromine can add. So it's a two-step process. So because of that, we're going to have a higher activation energy. But then look at the product levels. Here's our 1,2 and here's our 1,4. Our 1,4 is at a lower energy level overall. The reason why it's at a lower energy overall is because the alkene that it produces is more stable. This alkene is di-substituted, and this alkene is only mono-substituted. Way back when we learned about alkenes, one of the things we said is the more substituents they have, the more stable they are. So because it has more substituents, it's going to be at a lower energy level. So what does temperature have to do with this? When we are at low temperatures, we're only providing the reaction with a small amount of energy, probably just from stirring it. And it's not going to be enough energy to get over that big hill to make the product for the 1,4. So the only reaction that's going to form will be the one that forms the fastest, the one with the lowest activation energy, and that's going to be the 1,2 product. So the 1,2 product is the major at low temperatures because it has the smaller activation energy, and it's the one that's kinetically favored. So that's really just another way to say it forms the fastest. When we are at high temperatures, we are giving the reactions all kinds of energy. So both products are going to form. But what happens is when both products form, we have this 1,4 product, which is at a very low energy, and the 1,2 product, which is at a little bit higher of an energy. And it's at a high enough energy that it can actually go in reverse. The 1,4 product can't go in reverse because it's already so low in energy, and that activation energy was so high that that hill is just too big for it to overcome. But the 1,2 can go in reverse. So now when it goes back over the hill, it can go through either pathway. So really you can kind of wait this out. So the 1,2 keeps going in reverse. You can almost think of it like a 50-50 shot. It has a 50-50 shot of going through either pathway. If it gets into that 1,4 pathway, it's stuck down there. That's sometimes called an energy sinkhole because it's too low in energy to get back out of. But if it goes into the 1,2, it can just go in reverse yet again. The catalyst question I see there, Natasha asked if we have to look out for catalysts. We don't really use catalysts with this one because heat is definitely a good enough source of energy to have it happen. So good question, but because that will change our activation energy as we know, but no catalyst for this one. This is called the thermodynamic product. So it's pretty much all of second semester general chemistry. You talk about kinetics and thermodynamics. Thermodynamics is when we talk about the start and the finished energy levels. So by saying that it's thermodynamically favored, that just means that it's the lower energy product. And when we say kinetics, we're talking about the middle of the graph. We're talking about how high of that activation energy it is. So we can label it as the thermodynamic product because the product is low in energy. So that is all of second semester Gen Chem summed up into 2 sentences. So let's do one more practice here. This is definitely where we're going to be ending today. So we're going to react this, and we're going to react it with Br2 this time at 0 degrees Celsius. And I'm going to number all the way down the chain. We're going to draw both products. We're going to draw the 1, 2, and we're going to draw the 1, 4, and then we'll talk about what is the major, what is the minor. I'm going to draw just the chains here because that's not going to change. When we look at the 1, 2 product, we're going to add a bromine to 2 carbons. So for that 1, 2 product, where are my bromines going to add? Which 2 carbons? And you can put it in the chat. They will add to carbons 2 and 3. So bromine and bromine. And then that double bond between 4 and 5 stays put. So what about the 1, 4? If I'm going to add it to right here to start with, where will the other bromine add? Which numbered carbon? So it would add to the 4th carbon in relation to that. So 1, 2, 3, 4. So it's carbon number 5 on my label up there. And then our double bond is going to be right in the middle. So when we look at the 1, 2, we're always going to add it to just a double bond, ignoring the other double bond. And when we do the 1, 4, we're going to add it to the first and the last of our conjugated system, and the double bond moves to the middle. We are at 0 degrees Celsius. So which one of these is going to be my major product? The 1, 2 or the 1, 4?
The 1, 2.
Good. Okay. I think we're about at time. There we got like a 1 minute left. Any questions on this reaction before we?
I do have a question.
Yeah.
This might seem like a dumb question, but for the major, how it's 1, 2, I was just wondering, why is it labeled 1, 2 when the bromine's attached to it? It's not attached to the first carbon, it's attached to the second and third.
So when we have a long chain, and I numbered every carbon in this chain kind of to prompt that question, but also just to have carbons to talk about. But when we look at our big long structure, we only care about those 4 carbons in that little box right there. And so you could label those just as 1 through 4, because really it's the only those double bonded carbons that we care about. I numbered the full chain 1 through 7, just so we could kind of look at the entire structure. But the only ones that are going to be participating are the double bonded carbons. Another way to think about it is when we say 1, 2, it doesn't have to be the first carbon in the chain. It just has to be the first carbon in that conjugated portion of the chain. Does that make sense?
Yeah, so we're starting to count from the very first pi bond to the last pi bond.
Yes. So if I cross these out, we could say 1, 2, 3, 4.
Got it. That makes sense.
Okay. Anything else on this one, guys? Okay, so Wednesday we will start with pericyclic reactions. We are going to meet for lab today to talk about our first Beyond Labs virtual chemistry lab. So log off, go click on the other Zoom link, and I will see you over there in a few minutes.
Professor?
Yeah.
Could you go back real quick to that first thermo slide with the
Crazy one? Or one more?
The one, yeah, the last one. The one before that, I mean.
This one?
Yes. Let me take a picture of that.
Go right ahead.
Thank you. All right.
Professor, I had a few questions on the molecular orbital theory, if you didn't
Yeah.
mind. Okay, so I understand the concept of the Lumo and the Homo, but we actually didn't even go over like this in depth for Dienes for chapter 15. So like I'm kind of like learning along with him. But so the concept of Lumo is that it's the lowest energy molecular orbital.
It's the lowest energy molecular orbital that doesn't contain electrons.
And then what information does that give us?
It's going to tell us, so the reason why those two get labels is because those are the two that are going to take part in reactions. So if that molecule is going to be the one that's like reaching out with its electrons to bond to something, it's going to be the electrons from the HOMO. And if it's the other way around, like a nucleophile is going to come and create a bond, the new electrons will go into the LUMO.
So basically the LUMO is the most capable of accepting electrons?
Exactly. And then the HOMO is the most capable of donating electrons.
Could you go over how you identify the difference between the two HOMO and the LUMO?
Like when we look at a molecular orbital, you mean?
Yeah.
Oh, wait, let's see. Let's go back here. So the easiest way to do it is we're literally just cutting this in half. So half are going to be our anti-bonding above, and then the other half below are the bonding orbitals. The very first anti-bonding orbital will always be the LUMO, and the very last, or the top bonding orbital, is going to be the HOMO.
Is the differentiation between the bond and the anti-bonding the overlap or the orientation of the molecular orbital? Like when it's like the electrons are like sideways versus like standing up? Is that how you differentiate between anti and bond?
Not really. It gets into like a lot of calculus-based theory, like what's the word? Like computational chemistry is its own field, and that's really where it's headed with this. And so it's kind of also becomes kind of a numbers game. So what we're looking at here is 135 hexatriene, which means it contains 6 carbons, which means there's 6 atomic orbitals, which means it makes 6 molecular orbitals, which means there's 6 electrons. So if we do 1, 2, 3, 4, 5, 6, that means all of our bonding orbitals are filled and all of our anti-bonding orbitals are unfilled. Or another way to say that is that the bonding orbitals are occupied and the anti-bonding orbitals are unoccupied. And so based off of that, we can always say that whichever bonding molecular orbital is the highest in energy, it will always be the HOMO, and whichever anti-bonding orbital is the lowest in energy, it will always be the LUMO.
And then for 0 node and 1 node, I was reading in the textbook about the overlap of the, like, for example, and this would be like carbon 2 or carbon 3 starting from left to right. What overlap what does that signify aside from the fact that the single bond between them is shorter?
So the overlap is really saying that there's a bond there. So these are only looking at the p orbitals. So for our structures, we're looking at like the pi bonds. So essentially it's saying that these do have pi bonds between those carbons. It's a little bit hard to relate it to things we already know. So with this one, I could draw the different structures and essentially say, so it kind of represents this, but we can't even do that with this one. Oh, sorry. With this one, because there's too many carbons, and that's enough to actually make it not quite match up. So I'm not really answering your question because it doesn't relate to other things. So we can't relate this to the way we already think about bonding. It's its own thing. So really it's just a way to say that it's when they're all lined up in the same direction, we can overlap all of those orbitals, which is essentially saying that we can have resonance all the way across, which makes it lower in energy. But if those orbitals are flipped, then they're repelling each other instead of attracting each other, which doesn't have an equivalent in Lewis theory. So we can't relate it to what we already know, which is of course what we want to do, and it's what makes it a little bit complicated.
Okay. My last question would be, how do you think you would ask this, for example, on like an assessment? Because like the textbook only has like 1 or 2 examples even regarding this molecular orbital theory that I could find. And their question was draw an energy diagram of the relative energy levels for some dying and identify the Homo and Lumo. So do you think that's like an adequate practice for like?
Yeah, I'd have to look to see exactly how it's worded in the book, because I wouldn't have like what's drawn here in what was in like black and white to start with. That's what I would give, and then ask questions about it or have it filled in. But I wouldn't
Ask for an energy diagram.
Yeah, I wouldn't ask you to draw the energy diagram from scratch. I would at least give you all of those empty p orbitals just to have kind of like a coloring book version to start with. Does that make sense?
So the energy would be the lowest at the 0 node bonding, right?
Yes. So this is in energy level. So number 1, MO1 is the lowest in energy, going up to number 6.
Thank you so much. I appreciate it.
You are very welcome.
Have a good one today.
Bye.
Thank you.
All right, I am going to move over to our lab link.